Welcome back, everyone. Hopefully everyone's had a go at some of the exercises. Don't worry too much if you haven't completed all of them yet. You can always go back to them later as you learn a little bit more about the Idris 2 internals and just in general programming in Idris. You'll be able to go back and try them again. Also, it's not a massive worry because I've implemented them in Idris anyway. It's a matter of your own understanding of how the internals work, and it's entirely possible that if you were to do various kinds of extensions or transformations, say, or optimizations, that you may have to write more things of the same form. So occasionally I still have to. So that it's not a requirement for your understanding of today's lecture and what's coming next that you have those completed. That's basically the point. Okay, so if what we've done so far is it's been a kind of top-down approach to seeing how the overall tiny Idris system works. So we've started with this bird's eye view of the problem we have to solve. Yesterday we looked at some of the core representations, or particularly the core representation of terms. So today we're going to go a little bit further, a little bit deeper, using that core representation of terms, or getting towards that core representation of terms by taking some input that some programmer has provided and applying some type checking rule, the type checking process, to get to those well-typed, well-scoped terms. So I've kept changing my mind about what should go in this lecture. I've been trying to think of the most important things that you need to know in order to contribute useful things to the Idris core, and in order to kind of extend it in ways that might be interesting to you, or in order to try your own experiments with your own systems. So I was thinking, should I look closely at evaluation, or should I look closely at conversion? And in the end, I've sort of arrived at, well, what do you need to know? Where do we need to go in order to implement the elaborator from the beginning? So we'll try writing the elaborator, but we're going to need a few components in order to be able to do that. So I'll tell you about what those components are, not necessarily the details of how they work, but I'll do a little bit more of that tomorrow. But we will see how to apply those components and put them together into a working elaborator. So today, I've still got some exercises for today. They're not quite the same form as the last couple of days. So basically what I've done is I've taken Tiny Idris v1, because we're now putting a lot of components together, so it's good these things in the context of Tiny Idris v1. And I've removed some bits, just a couple of bits of the elaborator, replaced them with holes. And your job is to just a couple of examples of elaborating binders. So by the end of this lecture, once you've looked at the typing rules and once you've looked at some examples of how elaboration works, you should have some idea of how to do those components of the elaborator yourself. And if you're up for a challenge, I guess what you could do is just delete more of the code and try to, as my primary school teachers used to say, rewrite it in your own words. It's a good exercise to do. So we need to think about TT and its typing rules. So yesterday we looked at the TT syntax. Today we'll see what it means for a TT term to be well typed. So I'm only going to look at terms. I'm not going to look at declarations and data declarations, because in the end those things are really just about applying the term elaborator in a few strategically chosen places. So we're going to look specifically at elaborating terms, and with any luck, once you know how to elaborate terms, you'll see exactly what's happening when you look at the code. So we'll need to look at what the TTIMP representation itself is. So the TTIMP syntax you've basically seen. So looking at Tiny Idris, that is your TTIMP syntax, and it's mostly a very cut down Idris. We'll need to think about evaluating expressions. So there's a tricky problem with writing an elaborator for a dependently typed language is that there are points where you need to evaluate things, and you need to evaluate things that are already well typed. So you need the type checker to work before you can evaluate anything, but you can only evaluate well typed things. So my approach to tackling this one in when I was writing Idris from the beginning was to, it's a kind of classic agile approach. You do the minimum viable product, or product is a strong word, the minimum viable prototype. So just have the tiniest language with only one construct, or with like just a couple of constructs. So just have the type of types, and just have lambdas. And then everything else, this is actually something that's really, I find really handy about Idris. Everything else that you have, every component you haven't implemented, you just leave a hole, and it will happily compile things with holes. And just as long as you don't, as long as you write a hole for the normalizer, because there might be some, or there certainly are some typing rules where you don't need it. That's generally the way of resolving this chicken and egg problem for me, was to leave a hole for the thing that I haven't done yet. So anyway, we need to think about values. We need to think about how to turn terms into normal forms, or head normal forms. I'll say more about what that means later. And then once we have that, we're able to put it all together, process turning TT-imp terms into one of these well-scoped term representations that we saw yesterday. So just as a reminder of what TT term syntax actually is, so we've got variables, we've got binders. I like to group all the binders together. If you did some of the exercises yesterday, one of the ways you'll have found them easier to do would be to implement a map and a traverse for the binder data type. So you really can lump all of these things together. So that's a very handy thing to do. And then we've got applications, and we've got a couple of primitives. So we're just going to look at what the rules are for the different kinds of constructs that we have, and when we're looking at the rules, we'll treat the binders separately, and so we'll treat lambda and pi separately. I won't worry about pattern variables and pattern types in this case. We'll just look at lambda and pi. Okay, so what do we have to do in order to type check this thing? So throughout the system, you'll see this in the type signatures for almost everything. Once you get into the real manipulation of well-typed terms, you'll see that everything is implemented, or everything is carrying an environment. So an environment it's little more than a list of binders, in fact, and this is how, it's one way you might write them down. So this is how I wrote them down in the JFP paper that describes the core syntax of Idris. So environments can be empty, so an empty environment is a valid environment. If S is a type, then the binder lambda x of type S, that's a valid environment. And then similarly, if S is a type, then pi x of type S is a valid environment. So environments are storing binders. In full Idris, we also have lets. That complicates things a little bit, because when you're evaluating and you look up something in the environment, you also have to look up the value. But it really just adds one more thing to do. It doesn't add any kind of fundamental complexity. So there's all of the rules are relative to environment, and all of the, or many of the bits of the implementation that you see, you'll see this data type env, and because I think I said a couple of days ago that one thing I've learned about dependently typed programming, or type-driven development, maybe it's as the kind of programming methodology, is that once you've come up with your core representation, so the data type of all of the things of interest in your system, once you've found the right index for that, so that the right things to parameterize it by, it turns out that lots of your other data types, the need for indices and parameters on all of your other data types kind of arises naturally from that. So the fact that we have well-scoped terms with the list of names in the type means that when we define environments, we have to explain in the environment what each thing in the environment is scoped over. Because if we don't do this, well, we're stuck. We just can't have environments without doing this. So I like to I like to parameterize things. I like to make things generic in whatever seems to make sense. So it might be that environments carry things other than terms. So in this form here, in these rules, the environments are parameterized by terms. It might be that sometimes it's useful to have an environment of values. Sometimes it's useful to have an environment of other syntactic constructs. So I've said an environment carries anything that is any well-scoped type. So an environment could be empty. An empty environment, if it doesn't have any variables in it, it's not describing anything. So there are no names bound in this environment. If we add a binder to an environment, so we have an environment that has some variables in it, and we add a binder, then that will give us an environment with one more binder in it. So it's worth thinking about where binders come from. When does an environment get bigger? So when you, for example, have a lambda binder, remember the type of lambda or the type of binders in our well-scoped representation. The scope of that binder has a list of names x cons vars, and that naturally corresponds to what happens in an environment. As you go under an environment, as you go under binder, the environment gets bigger, and so this index exactly corresponds. So is it a coincidence? Not really. That's just it's just what happens. That's just how binders work. So this is pretty convenient because it means every time we have a well-scoped thing and we have an environment, we can see that environment, like subspecific environment, corresponds to this term. So we're not going to use the wrong environment for the wrong term. You might think, I don't make that mistake. Well, I certainly have made that mistake. I've made that mistake lots of times. It's nice to have the type checker point it out when I do. Right, so we'll see a bit more of this later on. So the other thing that we need to think about when writing the type checker is the conversion rule. So what is, if we've worked out the type for a term, how might the type convert with other types? So just to give an example of that, if I've type checked that something is a vector of 5 integers, and somewhere else I've type checked that a thing is a vector of 2 plus 3 integers, then those are not syntactically the same type, but they have the same normal form. They both have the normal form vector of 5 integers. So these two things are convertible. And so when we write down the typing rules, we don't we need to take into account the fact that two types might be syntactically not the same, but their meaning might be the same. So the rule is, if in some environment, so remember this gamma just stands for one of those ends that I've just shown you. So I usually like presenting things in code. I find things a lot easier to understand when presented in code. But this is how the code maps to the way you would typically present a type system. So just how to interpret this. So if an environment shows that x has some variable has type s, and the environment shows that some other t is a type, and s and t relate according to this conversion relation. So think of this conversion relation as being an intuitive way to think about it is s and t have the same normal form. It's a bit more precise than that. It's I've seen various ways of defining this. One is to say that you can get from s to t by applying a sequence of reductions and reverse reductions, and you will get to t. But in terms of how you implement it, it's normally these two things have the same normal form. Or these two things are either syntactically equivalent or have the same normal form. So if x has type s and s and t are convertible, then x, you can also say that x has type t. So there was a question.
Yeah, so question in the chat. In the environments we store lambda versus pi. That's just storing where the bound variable comes from, right? There's no other use for it apart from some kind of sanity check or.
So the reason the reason I store these as binders rather than specifically a name and a type, because in most cases, all you're really interested in is what the type is when you're looking something up in the environment. It's handy to store this as a binder. It's a bit more extensible because when you scale up to having let bindings, you could then look it up and say, well, not only do I know its type, I also know what it reduces to. So the evaluator might need to know that. So typically the type checker only needs to know its type. And I just find this as a neater presentation of it. It's because I can be consistent in saying I will deal with all the binders together. That's all. So different people present this in different. You will sometimes just see a name and a type in an environment, for example. So I've written these. You'll see there's a reason we write these typing rules using Greek letters. It's just because you can get the idea across much quicker and more precisely. But this is just to say what I've just kind of said in English. If X has type S and S and T are convertible, and it's okay for the purposes of this to treat convertible as meaning they have the same normal form. It's not the most efficient way to implement it, but it's a way to think about it. If they have the same normal form, then you can also say that X has type T. So that's a useful thing to have because it means writing down the other typing rules is shorter because we can just assume that conversion happens where it needs to. When it comes to implementing it, we're going to have to actually do this conversion check. But when we're writing down the rules, it's nice just to get a picture of what's going on. Right. So move on to the other rules. So for variables, if we're type checking a variable, we look it up in the environment. So what is the type of that variable in the environment? That will tell us what the type is when we type check it. What about application? So application is the first interesting one to look at. So if we have some function, so we'll type check our function expression, as long as that comes out as being pi x in S goes to T, and as long as the argument type is also in S, remembering that when we check it, we might have to convert it, we might have to apply the conversion rule to get it to be an S, but as long as somehow it becomes an S, then we can do F applied to S. And this is somehow this is almost the essence of dependent typing, in that when you apply a function, the return type of the function, or the thing the function returns, might depend on the value you give it. So the return type of F, the thing that makes dependent type checking interesting is that, maybe a bit more challenging, is that not only do we get this T, but the T might involve this variable X, so we're going to need to substitute S into X. One way or another, however we choose to implement that. So yeah, if F has a function type S arrow T, so X in S, S arrow T, so I'm just writing the binders in the TT form here, and if S, little s, has the argument type big S, then F applied to S has the result type T with S substituted in for X in T. So when we type check it, we'll basically type check the F, we'll type check S, we'll check that these two things have convertible types, then we'll synthesize a type for the expression by taking the return type of F and feeding in the argument type. So we also need to type check binders, so we need to check function types. So for function types, because we have binders here, we go under binders, and the return type of the function could use this X, then when we type check T, we need to have X available in the environment. So that's what we write down in the rules. We'll find out when we come to implement this, we'll find that we can't even implement it if we forget to add X to the environment. So because we've written down this this well-scoped representation that's precise about the names that we're working with, you'll find that you cannot implement a type checker for this language and forget to add this to the environment. The machine won't let you do that. I think even little things like that I find really neat when I'm working through this, because you really do forget these things sometimes, and it's nice to know at compile time. So yeah, if T under those under that constraint is a type, and as long as S is a type, then pi x in S rho T is also a type. So as long as the type of T in an environment extended with X and S is a type, and S is also a type, then the function type is a type. Lambda is similar but a little more complicated because, well, lambdas are typed with pi's. So I'll give the text first. So just like in the pi, if we extend the environment with some x of type S, and we check that E has type T, and if we also check that this type x in S arrow T is a type, so as long as we know these two things, then we know that lambda x in S dot E, so the whole expression we're checking, has this function type. So yeah, so when I'm writing these rules, by the way, I was sort of in two minds as to whether to go on to a digression about bidirectional typing rule presentation and bidirectional type checking. I'm just going to mention that that's a thing that exists. So bidirectional type checking is where I'm going to kind of very briefly summarize this as saying sometimes you can syntactically know that you have the type available. And you can use the type that you have, the expected type that you have available, to check the thing to check the expression that you're checking. Sometimes you know that you won't have the type available and you need to synthesize the type. So in the case of function application, you need to synthesize the type. In the case of a lambda, you will typically have the type up front, so you can get the type of the argument, for example, from the type that you're checking. This is a really nice way to present and reason about type checking rules. It simplifies quite a lot of things. It certainly simplifies reasoning about type systems. It's quite a nice way of implementing a type system and getting a certain amount of inference for free. The reason I haven't done this with Idris 2, well, there's two reasons. Firstly, the reason is I didn't do it in Idris 1 because back then I didn't know about it. That's the bad reason for not doing it. And I think possibly good reason is that we don't necessarily know in the surface language of Idris what information we're going to be given by the user. So I'm trying to allow a bit more inference than even bidirectional typing rules might give you. So rather than presenting this in this bidirectional style, I'm just presenting the rules as the things that need to be satisfied in order to be able to type check it. And then when we write the elaborator, we'll find that sometimes we have the type available, which really helps us, and sometimes we don't, in which case we might have to infer something. We might have to synthesize it. So bit of a digression on bidirectional typing. If you don't know about it, I highly encourage going and reading about it. Just to say, we don't do it really in Idris. There's a ping. Someone has a question.
Hi. Yeah, I am confused with this rule because so in the right hand, well, in the right portion of the assumption, pi x is of type S arrow T. Is itself of type. I think something is wrong. The typo.
It's not that pi x is of type S arrow T. It's that this is a function binder. It's like for all x in S, T. So this might actually be a bad choice of notation. Do I have? So it's like this whole thing here. Imagine a function type S arrow T. So we start with that, and then this is saying that actually S is called. We'll give the name X to S, and X might appear in T. So it's kind of like saying well, if you say if we take this bit here, so lambda x in s dot e, that's saying we are binding an x with type s, and x is available in the scope e. So this is the same. So we're binding a variable x of type s, and that's available in the scope t.
Oh, well, that's.
So I think
that's a very confusing syntax.
I think this is maybe a bad choice of notation. Maybe I should have put a dot there instead of an arrow. I was trying to make it look a bit similar to the surface language, but by asking that question, you've convinced me that that's a mistake. So I think after this talk, I'm gonna update this notation to make it a bit clearer. So thank you for that. Yeah. So. Yeah, that's saying if the type of E in an environment extended with x is t, and the function type is indeed a type, so that would be checked by the previous rule, then the lambda binding has type function from s to t, or function from x in s to t. And digression about bidirectional typing, if you like, that sort of thing. So yeah, just because I'm not using bidirectional typing doesn't mean I don't think it's a good idea. It's that I haven't found it necessarily that useful for an elaborator, but it might be that it's a direction that we could go. Anyway, now then, that's the typing rules for other. That's the kind of the most important components of the typing rules. So I haven't given them in full, but you can. So I haven't looked at the type of types, for example, and the types of the primitives. But that's the typing rules for applications and binders, which is the ones we're going to look at more closely. So now that we know those, we need to somehow implement a system that checks whether a TTIMP program that has been written in a text file is valid according to those typing rules. And so for today, we're just going to think about how we check a thing that has been written fully explicitly. Tomorrow, we'll take that a bit further and think about how we extend it to have a bit more inference. So how we extend it so that a user could put an underscore in to mark, you work this out. But yeah, today we'll not worry about that. So TTIMP is basically it's a desugared Idris. When I say desugaring, I'm really saying that full Idris is literally is syntactic sugar for TTIMP. There is a module as part of the full Idris2 system. It's a file idris.desugar, and it's a syntactic transformation of the input program. Everything you see in the surface Idris language has a more or less direct translation down to TTIMP. It's a little bit more complicated when it comes to interfaces and implementations of interfaces. So there's a little bit of context that it needs to look up to find out what the methods are, for example. But basically, it's a syntactic transformation. So we don't need to worry too much about that for the purposes of what we're going to say today. But I do want to mention it because I think it would be really interesting to try front ends to TTIMP that take a different form from Idris itself. So some of the things I've had in mind that I'd like to try in my copious free time. I'm intrigued by the idea of an imperative dependently typed language that uses TTIMP as the core, because we've got do notation, and maybe by some kind of CPS translation or some kind of static single assignment translation, maybe you'd be able to translate it to come up with some TTIMP constructs that you translate down to that allows mutable variables. Maybe you could take advantage of linearity to do that. I'd be interested in a language with dependent types and effects, so a high-level syntax for declaring effects. Some kind of syntactic support for linearity. So we haven't looked at that in this course, but when you're writing functions that have linear inputs, you have to return the input as well, like the updated input as well sometimes, and that's kind of annoying. I'm not going to do any of these in Idris2 itself because it's already a big enough language, but just in case that inspires anyone to look at different surface languages that use a linear QTT core, I think that would be a very worthwhile thing to do. Right. So the challenge now is we have to figure out how to check TT-imp programs, and to some extent, in some cases, infer types for TT-imp programs. So there are a few more things we need before we can do this. So firstly, I've already mentioned this. Everything happens relative to an environment of local variables. So when we start checking at the top level, that environment is going to be empty. But as we add pattern variables, as we add lambdas and pi's, that's going to get bigger. So we need to track how that environment is growing while we check our TTM program. We also need, we also have global names available. So this is something that in the rules I've just presented, we've kind of treated the gamma as capturing all of the global variables, all of the local variables. So we've kind of been treating it as functions are lambda expressions, and as you add more functions, you're just going in the scope of that lambda expression. What we actually do, this is just a pragmatic thing, is it's much more convenient to have a global context, because you might be reading things from files. You want to look things up in that quickly, so you don't necessarily want to be counting back an index of how far along in the environment it is. So that global context contains type constructors, data constructors, function declarations. It also contains a couple of other things that we'll get to a bit more tomorrow. So it contains holes. That's things where we have a type but we don't have a definition yet. It has call them guesses, which worth saying actually, the Idris 2 Elaborator is modeled, and the way it does unification is modeled on Ulf Norell's thesis. So it's Idris 2 is to some extent another implementation internally, another implementation of an early version of Agda 2. So Agda's gone in different directions. No doubt Idris 2 will go in a different direction, but basically following the same sort of structure. And I can't remember what the terminology that Ulf used. It might have been guesses. But guesses are things where we have a definition, but it's only going to be a valid definition if certain unification constraints are satisfied. So they also exist in the global context. But essentially, think of it as being type constructors, data constructors, function declarations. Later on, it's also going to contain solutions for meta variables and constraints on meta variables. So this is what it looks like in code. So we're going to move on from rules to how it looks in Idris code now. I've got to a point now where I'm far more comfortable looking at the code than I am looking at the rules. I guess I always was more comfortable looking at the code than looking at the rules. But this is what we have. So a definition is either not ready yet. So when you write, when you give a type declaration, it's perfectly valid in Idris to give a type declaration and no definition. So the expectation is that something that has the definition none is at some point going to get that definition filled in. But this is for something where you have made the claim and there just isn't an implementation yet. So the functions that you write, the pattern matching functions are going to be represented in this form. So remember yesterday we saw that functions are, I'll get to that in a moment. We saw that functions are left-hand side equals right-hand side, and then they get compiled down to case trees. So once they're compiled down to case trees, we represent them in text as the arguments they've got, and then a case tree that is well scoped relative to those arguments. So yes, there was a ping. Please go ahead.
What's the difference between having a none definition and a whole definition?
Good question. I thought someone might ask that. So a whole is something where in the program, if you write query something, query in a name, that's a whole. Whereas if you have a top level type declaration, so you just write foo : type, that will come in as none. So the reason for the distinction is the way that these definitions none and whole get treated. So there's two ways off the top of my head I can think of where it differs. So if you try to write a definition, like pattern matching definition for something where the existing definition is none, then that's okay. It will fill in the definition. If you try writing a pattern matching definition for something where it looks it up and finds out it's a whole, then it won't fill it in. It won't accept that. It will say, no, this is a whole. You can't write a pattern matching definition for that. There's an argument that it maybe should allow that, but it doesn't. And the second thing, it's not part of Tiny Idris, but it is part of Main Idris. When you have have a whole in as part of a bigger definition, that whole will have a few local variables in scope, and the whole might itself have a function type. The overall type of the whole is just the whole function type. It's all of the local variables as pi binders, and then the rest of the type as pi binders. So it records how many of those names are names that you gave, and how many of them are actually the type of the whole. So it has to know. It's really a display thing. It has to know where to stop printing the premises and where to start printing the type of the whole. So that's just a kind of internal representational difference. So yeah, there's not a whole lot of difference. It's just there's a couple of things where we behave slightly differently, so it's convenient to have two different things. Okay, so we've got pattern matching definitions. We've got data constructors and type constructors, and yeah, whole and guess I'll tell you a bit more about tomorrow. It's worth saying what tag and arity are. So tag, when you define a data type, every constructor gets an integer tag associated with it. The integer tag is used as part of the case tree. So we dispatch on an integer tag rather than looking at the name of the constructor. And it doesn't make a huge difference to performance at compile time, but it is something that's valuable at runtime. So at runtime, we'd ideally compile a case expression into a jump table rather than a series of if expressions looking at a string for the name. So the tag is an integer saying which of the constructors it is, and then the arity, that's the number of arguments it's expected to have. So though in a dependently typed language, you can have variadic functions. So you can compute a type that just gets bigger and expects more arguments. With constructors, they're always going to have a known arity, and that, again, it's just something that's convenient to know. We can calculate it from other places. It's just a convenient thing to have available without having to look it up. Again, it's about interactive editing to some extent. It's about compiling. Yeah, someone else has pinged their hand up. So
the arity is relevant and irrelevant arguments, right? So you're not doing anything fancy here yet. This will come later.
Yeah, it's all of them. Why is it all of them? I can't remember. Sorry.
There's another question. Why int, not nat?
Good question. I don't know. It probably should be nat. Because it's never going to be negative, so perhaps it should be nat. Yeah, good question. I'm tempted to say that as I've been preparing these slides, I've come across occasional things. So this isn't one of them, but I didn't think of that at the time. But I've come across occasional things where I think, well, maybe that's not the right name for that data type, or maybe there's a better type we could use here. And I've decided in the end to go with what's in the Idris 2 code as a tiebreaker, just so that you see what is there. But I'm also going to say, if you see something that you think could be done better, please just do it better. If you think there's a refactoring that just makes something cleaner or neater, I'm absolutely happy to accept that. Sometimes people talk about the campsite rule. You know, when you're working on the system, leave things a bit cleaner than you found it. So you know, don't completely tidy up everything. But if you see a little corner where you think it might be neater for that to be a nat, I don't think it would break anything it wouldn't break anything to turn it into a nat. Okay, let's move on, because there's no way I'm going to get through all this material today if I don't. So we need to represent the global context. So all that is a map from names to global definitions. So global definitions are, every definition has a type, So we've got this record saying, well, everything about a definition, everything has a type and it has a definition. In full Idris 2, there's a load more stuff in here. So we need to think about the call graph, size changes for termination checking. There's search hints and all kinds of other things. So it's the reason I've put this as a record here. But we'll generally be looking up. Also the multiplicities of things and all kinds of other stuff. As just to say, this is the thing that you will be looking up values from the whole time. Right. So TTIMP. What does TTIMP look like? What's the syntax for TTIMP? So this is what your textual expression code will parse into. So we've got variables, we've got binders. So in the case of I haven't got the binder type in this case, just because we're talking concrete syntax here. So there's various different ways of writing pies and lambdas that don't quite map directly necessarily to what you'd write in with a binder, and we're going to have different typing rules for them anyway. Pi binders, lambda binders are going to type check in different ways, even though they end up in this thing that is generic in binders. So pies, lambdas, pattern variables. We have applications, we have implicits or holes, and we have the type of type. I'll mention one thing that's slightly different in Idris 2. We don't have padvar in Idris 2. We have instead something that's called ibindvar, where you give a name that is not expected to be bound. When it comes across that during type checking, it knows what type it's supposed to be, because we do have the expected type while we're type checking. So we do feed in the type that we expect for an expression. So when it encounters an ibindvar, so this is like when you have an implicit in a type variable in a function type, that will be an ibindvar. When it encounters it, it knows what type it's supposed to be, so it will add it to the environment. So it's a slight extension, but it simplifies things for this presentation just to have pattern variables. Okay, so that's fairly conventional representation of a syntax tree. So what we need to do is use this machinery that we've got to turn in an environment some unchecked term, call it raw for untyped. And we've got an environment, we've got a non-type checked term, we've got an expected type. I'll say more about this glued in a moment, and that will return a pair of the checked type and what its type was, and the inferred type of the thing we were checking. So that is a glued vars. This is a maybe glued vars. So a glued is it's our representation of the result, the type of an expression that has been type checked. We might feed in nothing for the expected type. We might be expected to infer it. We might have it available, but when we finish type checking, we will have it, assuming we were successful. If you remember from yesterday, core is all of it's the in quotes monad that everything happens in. So core, there might be errors. So any type error, kind of any undefined variable, this could potentially throw an error for all of those things. So assuming it's successful, we'll come out with the type check term and its type. So there's a couple more things we need to think about before we can get on with this, which is, firstly, I showed you the conversion rule. So we check that a thing has a type, and all of our typing rules say, if the argument has type S, and the expected argument type is S, then we can go ahead. But we do need to think about conversion, because these two things might have had different types synthesized for them. So we need to think about conversion. And then there's this, what is this mysterious glued thing anyway? And both of these things are about values, normal forms. And almost anything interesting that happens inside the core, almost any of the manipulations we do end up being on values rather than on terms. So terms are the well-typed thing. They're the syntax, or the well-typed syntax of this type checking process. They are the things that we will turn into, that we will compile. But because type checking involves knowing about the meaning of things, not just the value of things, like the semantics of a thing. So all of those things, conversion checking, unification, that's going to be about the value of a thing. So what's a value? Now, when we're elaborating these programs, this very often involves, for various reasons, involves looking at how terms reduce. So if you have something of type where we've synthesized a type vect2 plus n, but we're expecting vect of suc of n of int, should say, are these two things convertible? They're syntactically different, but they are convertible because 2 plus n plus is written by recursion on the first argument, so it will reduce to suc of n. They convert. Also, when we're type checking a function, so we sometimes define type synonyms that expand to functions. So we might have natop being defined as nat arrow nat. When we're type checking a function, we need to know that natop is actually before we can even check that the argument is the right type, we need to know that this is a function type because we need to pull out the argument type from it. So we do this throughout by working with values, not by working with terms. Terms are just the thing that we're constructing as a result of type checking that as directly as possible corresponds to the TT-int that has been given. Values are the things that represent the meaning of a program. So it's a separate representation because, as well-behaved type theorists, we like to make illegal states unrepresentable. So it's nice if we have a representation where, just by construction, the thing we're looking at is guaranteed to be a head normal form. So there's no possible way that this hasn't been reduced as much as it should be. So what is a value? What is a head normal form? So it can be any one of these things. So it could be a constructor that's applied to some arguments. So a datacon or a tycon, data constructor, type constructor. So we'll know, at that point, we'll know what the constructor tag and name is. We'll know how many arguments it has, but we won't necessarily have reduced the arguments. I'm talking about head normal forms here. We know what's at the top of the value. We know what the head of the value is. We don't necessarily know what its argument is. So we only evaluate, during type checking, we only evaluate as much as is necessary to make some progress in type checking. So so this is, I guess it's done lazily. So the evaluation at compile time is done lazily. So evaluation at compile time and execution at runtime, they're very different processes. So there's very different constraints on the two things. So this is kind of inspired by, going back to the 70s, cons should not evaluate its arguments. We won't evaluate arguments unless we need to. So it might be a binder. So for the binder, we know that it's a lambda or a pi or whatever. So we know that, so we can look at the binder and pull out the type of that binder, which, by the way, will also be a value at that point. We know that the binder has a scope, but the scope is not yet reduced. We can, and that's kind of naturally because we can't reduce a lambda. We can't reduce the scope of a lambda necessarily until we know what argument we're feeding that lambda. We know that it's, when the value shows up, we'll be able to plug it in, but we can't immediately evaluate it. It might also be a stuck application. So by stuck, I mean if you try to evaluate plus x of 2, and all you know about x is that it's a name of type nat, then you can't go any further. So at that point, you have a value because that's all you know about it. So the thing at the head is a stuck function application. And the other thing it could be is any one of the primitives. So also it could be a meta variable. It could be a local variable. So one of these stuck applications could be of a meta variable. Could be a local variable. The most interesting thing it usually is a meta variable. So which we need to fill in during unification. Anyway, during type checking, we're going to, when we check the type of something, we are going to get it back as a value. So if we need to know whether something has a function type, for example, we'll look at the value, we'll see that it's a binder, we'll know its argument type at that point, but we don't need to look at the scope, we just need to look at the argument type to figure that out. And the good news is the representation means we won't even have evaluated the scope. We'll be ready to do it when needed, but we haven't. We haven't done it yet. So in code, what does that look like? This uses there's a few mutually defined things going on here. So I'll say what they are in a moment. And essentially, in code, this is just what I've showed you as that informal description. So we have data constructors that have a name, a tag, and an arity, and a list of arguments. So this list of arguments is a list of closures. So a closure, we're using this in the same sense that you would generally use closure. It's a pair of an unevaluated term and the environment that that term lives in. So when we need to make progress, like if we want to go further, if we want to actually evaluate what those arguments are, we'll need to know what the environment was at the point where we got stuck, and then carry on evaluation from that point. Same for type constructors. The reason these are separate is there's a couple of places where they're treated in slightly different ways. So you could possibly do it this. I mean, at some point you might want to turn a normal form back into an expression. So you know, there's times where you'll treat these two things slightly differently. So evaluation, you'll treat them slightly differently. So we have binders. So a binder is, again, we've used this parameterized binder type. So this is another place where having that generic binder type is handy. So the argument type itself is a value, but the scope of the binder, so this is slightly different. So in the scope of a binder for terms, the scope said that we have one more variable available. Here it's slightly different. The scope says the thing that we're this thing here, this function, this is a function that's computed during or calculated during evaluation that says how to evaluate the scope when you evaluate the argument that you're going to feed in. So when you evaluate the scope of a lambda and you know what the argument is, that's kind of like when you're doing the substitution. So some of you successfully implemented the substitution function yesterday. If you did, what you did was this traversal of the term, where you take a term with some number of variables, you plug it into a scope where there's one more variable. Well, this is a function that kind of does that job for you. So this is the thing to look up if you're interested in more of the details of this is normalization by evaluation. So it's having a function that describes the meaning of the scope when you get around to evaluating it. So when we want to know what this is, and when we have a value available, we'll just plug it in and we'll get an evaluated scope. So this shows up quite a bit during type checking. Well, we're not going to get to this today now, but we'll see when we're type checking applications an example of how this works. So applications, a stuck application, we've got something stuck at the head and it's got some arguments. So what's ahead? I'm just gonna skip through this because we're not going to need much more of this. I'm gonna skip ahead to what am I going to skip ahead to? I'm going to skip ahead to what a glued term is. So you've seen what a value is. Take it as read that there are functions that can go back and forth between values and terms. But going back and forth between a value and term is potentially quite expensive. If we're going back and forward a lot, we're changing the representation a lot. We might have to to read off a term from a normal form, we'll have to evaluate that scope with some free variable and then read back the term. So we'd like to avoid that if we possibly can. So when we're type checking, we don't necessarily know when we produce a result if it's going to be useful to produce a value like normal form, or if it's okay to just use a term that we've looked up. So if we're type checking a variable, we'll look up that variable in the environment. Its type will be term vars. That could be good enough. That might be all we need to know. It might be that we need to make further progress. It might be that, for example, if we're checking a function type, we need to know that something is in normal form. So we'll reduce it further, and at that point, the type that we have available is a normal form. So the point of a glued is to not have to make that decision. So I don't know where this idea of glued terms originated from. The first I read about it was a paper from 2005 by James Chapman and some others on implementing the core of epigram in itself. So type theory. The type theory should eat itself, is that what it was called? Anyway, I think it's going back to there, possibly further back. So it's basically deferring the decision of whether we use a term or a normal form until we actually need to know. And it's constructed from whatever of a term or a normal form we have available. It's converted to whichever of a normal form or a term we need lazily if we need to. So we build what's convenient. We don't evaluate to a normal form unless we have to. And we ask for the thing we need when we need it. I'm doing very badly for time. So what I'm going to do is revisit that tomorrow and just show you how one or two of the rules get elaborated, because that will give you enough to be able to at least start looking at the exercises. Right, so everything happens, all of the interesting things happen inside this check term function. So we've seen this type check term. We've seen what a glued is now. We've seen that we have the ability to look at values if we need to. What remains is we need to know if we've type checked a thing, if we've got a type for a thing and we've got an expected type for a thing, we need to know that those two things correspond. So tomorrow, my plan for tomorrow is to talk about how to do that. Talk about two ways of doing that. Firstly, just conversion checking, so the conversion rule directly is implemented. But secondly, a much more useful, a much more expressive variant of the conversion rule, which is, are these two things unifiable? So the difference between conversion and unification in the context I'm talking here is that unification will fill in meta variables as it's going, whereas conversion will just say yes or no. So the main distinction between Tiny Idris version 1, Tiny Idris version 2 is version 1 just does conversion, version 2 does unification, fills in the meta variables as it goes. So all of that happens, whether it's conversion or unification, happens in this function checkexp. And so every part of the elaborator, you'll see that they basically all finish with checkexp that says, okay, I have a term that I believe is well typed. So we have this is the result of what the TTIMP has turned into. I have the type that I believe is correct for it. So I have the type that I synthesized for it. And I'm also going to feed in the expected type that the type checker thought was, that we fed in when we initialized the type checker, the type that we think it's supposed to be. And checkexp, if these two things correspond, will return the term and its type. So the Idris version, Tiny Idris v1 version of this just checks whether these two things are the same. If the expected type is nothing, all it has to do is return what we fed it, because it's the one we synthesized. If it's an expected type, we'll check that they convert. And the Tiny Idris v2 version will unify them and potentially solve meta variables on the way. So we don't actually, it's kind of pleasing that when we have this function, in order to turn something with no implicit arguments into something that imports implicit arguments, pretty much all we have to do is change convert to unify. So it's obviously a bit more complicated than that, but that's the essence of it, turning convert into unify. So I'll show you one of the rules. I do appear to have misjudged the time on this one, so I'll come back to some of these details tomorrow, but I do want to show you, before finishing, I do want to show you how that application rule turns into code. And what I presented on the screen here, this is the complete implementation of the application rule. I've just deleted some comments. So what happens? So we've got f applied to a. We need to check that we need to know that f is a function type before we proceed. We know at this point nothing about f. It doesn't matter what we know about the expected type, whether we have something available or not. We know nothing about f. So we need to check that the type of f really is a function type. So call checkterm recursively. Don't feed an expected type. It gives us back the term and the glued variant of the type. I tend to use this Hungarian style, so G to say that it's a glued thing. Now, in order to make progress, we need to know. So when we've type checked f, let's say it's a name, we'll just have looked up the name in the environment. that'll be a term. If we're lucky, that term will already be a binder, so we can progress. But it might not be. And the only way we're ever going to know is if we look. So we pull out the normal form and check whether it really is a function type. If it really is a function type, that's brilliant, because now we know what the expected argument type is, and we can feed that into type checking A. So when we type check the argument, we say, right, I'm going to type check the argument now, and the thing we're expecting that argument to be is the type that we've just the type that we've just read from here. So glueback is just there are various functions for going between normal forms, terms, and values. So you just have to know what they are. So this will turn the type back into a glued thing. All it actually does is it stores the type that it's read. So we'll check that. We're expecting it to be this type, and that's all we have to do. So the final thing we need to do is this expected type had better be consistent with the type that we've just synthesized for the function. So how do we synthesize the type for the function, the complete type for the function? The complete type is going to be this scope with whatever the value for A was fed into this scope. So remember that a scope is a function that calculates the result. So it continues evaluation with an argument to substitute in. So that's what we do. We substitute it in the current environment, and that gives us the type that we've synthesized. And we're going to call checkexp that does the conversion check, saying, I believe the result of this is to apply the well-typed F term to the well-typed A term. The type I have synthesized for it is this scope prime type, and the type I want you to check that it's consistent with is the type that was fed in. So basically all you have to do to type check a function type. It's almost but not quite reading off what the typing rule says turned into code. So the result of just setting up all this machinery is that the typing rules, so those typing rules that I presented early on, it comes out at about 100 lines of code. I think it's kind of neat that a type checker that does the core typing rules for your system turns out to be quite small, and it's only quite small because we've done all of this work setting up the machinery to make it quite small. But it's nice that you can condense it into that small space. Gets a little bit trickier if you have implicit arguments, and not something. Yeah, I'll go into a bit more depth on that tomorrow. I think for now, I'll just leave this. I'll leave this elaboration of applications, and maybe what you could do is just take this slide. Look at this slide alongside the typing rule for applications and try to convince yourself that there's a correspondence between the two. Once you've done that, you can start seeing correspondences with all of the other typing rules, and you should be able to go ahead and implement them. Okay, so as usual, I've overrun, and there's a few more things I wanted to say today, but I'm gonna save them for tomorrow. But I'm gonna still tell you what those exercises are. I think if at least if you've seen this before, you may already have enough to be able to do these. So I've left, in the lecture 3 code, I've left check term incomplete. I've put a few holes in it. And if you look at the typing rule, see how the typing rules could correspond to the holes in those definitions. And take a look at, have a closer look at IAP, the IAP rule, to see how that might. And I'll finish off explaining the details of that tomorrow. So what has to happen tomorrow? I have to tell you a little bit more about values that I didn't tell you today, and then I need to show you how conversion checking and unification work. So the mysteries of checkexp. So checking that things work, it all comes down to what goes on inside checkexp. So the bulk of tomorrow is going to be about the mysteries of checkexp and how we are allowed to have implicit syntax as well. But yeah, for today I'll stop there, and thank you for your attention.
Yeah, I just wanted to ask, given that it came up, has anyone done like a study of lazy versus eager evaluation at type checking time? Is there kind of some clear reason for saying that laziness is kind of the best way?
I can only give you some anecdotal evidence on that one. I'm not aware of any formal study, but Idris 1 did it eagerly, and my experience of this is that most of the time it makes absolutely no difference, because most of the time you're going to need to evaluate quite deeply anyway, and a lot of the time you're not actually doing that much work. Unfortunately, that's only most of the time. Quite often you'll end up in a situation where, so two possibilities, and we can imagine this both in the context of the expression a million plus a million, where a million is a net, and it's been constructed just by conversion from an integer. If you do the check eagerly, you're going to have to evaluate a million as a net, it's going to take quite a lot of memory to do that. So if you have two expressions, a million plus a million, and another expression, successor of 999,999 plus a million, then it only takes one step of evaluation to figure out that those two things are the same. So once you've got the head, you know that the head of both is a successor, and then the scope is just 999, or it's on the scope. The argument of the successor is 999,999 plus a million, and they're both equal. And at that point you've won. So you don't need to go any further. So that's why, at least in these cases with lots of computation in the type, it appears to be better to use a lazy approach. The other reason is during unification. So you have a data type just is_suc. It's just something that so is_suc of n, and is_suc of n is you can only construct it if n happens to be a successor. So what can you construct is_suc of a million, where a million is constructed calculated from an integer. Again, if you do eager evaluation, you're going to have to do that complete calculation. Whereas if you do lazy evaluation, you succeed very quickly because you establish that it's successor of some big expression. So I have a few pathological cases where Idris 2 checks things instantly and Idris 1 takes forever. What I haven't done is any kind of rigorous formal study of whether that's actually true in the general case. So it's what I believe to be true, and by this, we really are doing less work. We are necessarily doing less work in the lazy approach. That's my justification. Is we stop a lot earlier, therefore it must be quicker. I have nothing more formal or scientific than that.
Yeah, I just worry with that justification because you can say that for sort of arbitrary programs, and we know that it's not clear that Haskell is the quickest language ever or something.
Yeah, and there's a lot of different things going on at compile time and runtime that would affect this. At runtime, you might be building a lot of thunks that you never evaluate. So the fact that we're doing reduction under binders, which Haskell doesn't, might make a difference too. So yeah, it is really only a hunch, and it's worth exploring deeply. And I think you would get the best answers if you did it with real programs rather than constructed, contrived things. So I think once we've built up a collection of interesting programs, ideally that do a lot of type level computation, I'd really like to know the answer to that more formally than my mere hunch. So yeah, we should do that.
Right, yeah, thanks for the answer.
There was another question. What's that?
Question from the chat. I wonder why.
Remembering that we're still recording. Are we still recording?
We're still recording, yeah. I wonder why Idris allow you to match on something of type, whereas say Agda doesn't. What are the implications of it?
Because I think in QTT, the fact that we have this explicit distinction between what's available at runtime and what isn't, so that's there as a quantity. And at that point, there is no longer any reason not to be allowed to match on types, in my opinion. Because the type is explicit about when you can match on types. So if you want the parametricity properties of something, it's not really anything to do with whether something's a type or not. It is to do with, well, whether it's a parameter. So we can say that in the type, and we can say it in a much more precise way than just saying this is a type or it's not. We do it by saying this is available or it's not. So the short answer to that is because we can, I suppose. Why Agda doesn't do it? Maybe they will at some point. I don't know. They've recently added quantities, particularly erase quantity, and whether that changes things, I don't know. Maybe they'll allow it. I should say that I haven't actually come up with a practical use for matching on types yet. Every time I come up with one, it always turns out that there's a better way that doesn't need matching on types. But I bet there's some interesting generic programming tricks you could do if you put your mind to it. But I'm not just going to gratuitously go out of my way to match on a type because I can, even though it's kind of fun trying the examples. Somebody will find something creative, I'm sure. That's another question.
Yeah, just to continue with what you were saying, so in C++, in metaprogramming, when you do compile-time metaprogramming, there are various times when you want to actually do specific optimizations based on the types that you're working with. And therefore, you would want to very, very vastly actually to do, type pattern matching on types specifically. So if that imaginary, bridge between Idris and the C++ metaprogramming is built ever, this would be a major, journey planner between the two languages.
Yeah, that's a good point. I've wondered about that because I've not explored this at all, but a while ago, so I think early 2000s, Stephanie Wyrick and some others did some work on intentional type analysis for that kind of optimization. I'm only dimly remembering it, but there's definitely scope for some interesting optimizations. Absolutely. So yeah, it might be a case of not of we need this in order to be able to solve a problem, but it might end up being we need this in order to solve a problem fast. That might be something that is used for optimization. Sure.
Well, not just the sometimes the efficiency, it's also a matter of correctness. So.
Okay.
So you might want to, for example, say that this kind of algorithm only works for representations of types that have that kind of memory layout.
Right.
It's not just efficiency; it's also a matter of correctness.
Yeah. No, there's a lot to explore there.
Really so.
Yes. Any others, or are people waiting for the recording to stop before asking?
Another question. How about this approach? Compiling, doing type checking, and then running the compiled code, then and there for conversion checking. Right.
So that's a very interesting question. The short answer is that it's hard. But people have done work along these lines. So there's an ICFP 2002 paper, if I remember rightly, by Benjamin Gregoire and Xavier Leroy on compiled strong reduction. So basically compiling under binders. So kind of what we do with our n-bind constructor. So just to pull that out again. So being able to compile these things and run them efficiently. And I read that paper years ago, and I thought it was lovely, but it would take a huge amount of effort to implement it, because you need to have access to a good runtime system. For example, you need to kind of hack into the runtime system to say, I want you to compile this, but I need you to know what a free variable is so I can read it back and turn it into my own representation. So I'm pretty certain that that's a good thing to do, and we should try it. But I also think it's a huge amount of engineering effort to do it. It maybe that someone just knows how to do that, and if someone knows how to do that, by all means have a go, because the evaluator is definitely the slowest part of the system. Well, it's the slowest part of the system, but it's the part of the system where more work happens. And the evaluator we've got is not tremendously clever. It's using some pretty standard techniques, normalization by evaluation in particular, and it's likely that creative ways of writing, better ways of writing the evaluator are worth doing. It's entirely possible that Scheme will help us. So some people have asked, since you're using Shea Scheme as a target language, and since you're compiling to Shea Scheme, could you take advantage of that runtime to do evaluation under a binder, because Scheme knows how to do evaluation with symbols? And I like that idea. That could be lots of fun to try. The one thing two things put me off it. One is, it's just a fundamentally hard thing to figure out, but also it would mean we were tied to a particular runtime. And something I enjoy about Idris is that you can retarget it relatively easily. So in the Idris system itself almost compiles to JavaScript successfully now. So it's not as fast as Scheme, but it just wouldn't work at all if we were then relying on a particular Scheme runtime. But that's a really interesting idea, and I would love to see it work. I don't really fancy doing it myself, but
maybe compiling the libraries for the type checker. But
right, yeah. So having things just rather than having things in this term representation, have things in a compiled form that evaluates quicker. That would be sort of halfway to the same thing, and probably a lot faster, a lot sooner.
Yeah, I'm just thinking if someone does a lot of type level computation, it might be nice to have in a library. It might be nice to have it compiled.
I can't imagine who might be interested in doing a lot of type level computation in a library. So for everyone else's benefit, Ohad is talking about himself here.
Okay, so there's another question. If Idris can build itself to JavaScript now or soon, is there a tryidris.com or similar in the works?
Oh, someone has. It was mentioned on the mailing list, and I don't know what state it's currently in. Something like learnidris.net. It's on the mailing list, and it does bits of interactive editing. I don't know if it's something that is requesting contributions yet, if the source code is available, but it's not done. I have no idea how it works, because I don't know very much about that level of web programming and that level of complexity of web programming. But you can do it. Be interesting to put the whole of Idris in the browser. I don't know if that would be the approach I'd take, but it's not beyond the bounds of possibility that could work.
Yeah, someone posted the link.
Oh, brilliant! Thank you.
So we have a question from Gecko.
Yeah, so just going back to my question about compiling during conversion checking. So you mentioned that you like not being tied to a choice of runtime, but this would only mean that you're tied to a runtime during compilation, right? So really only in this compiling Idris in the browser kind of situation would that be a problem?
Yeah. So it's not a huge deal. But it's not out of the question that later on we'll find that we get generally better performance if we abandon scheme and someone writes a really good LLVM runtime, for example, or OCaml runtime, or malfunction, and it would make that job a lot harder. On the other hand, if there is a significant benefit in doing it, then who cares? Let's do it. Let's do it the fast way. So it would have no problem with retargeting other programs. It would only be about Idris itself. So you're absolutely right there. We wouldn't be losing too much. But I think that this other point that having a different compiled form for library code, not even necessarily just library code, just things that are currently finalized, would be a quicker way to achieve this, and it would certainly be quicker than evaluating terms. And I think something I should have mentioned, because this inspired a lot of what I'll do a references slide tomorrow that points out all of these things that have inspired me. But Andras Kovacs has done some marvelous work on a system called Small TT. And some of the ideas in Small TT have inspired the way Idris goes about things. And again, we'll see more on this tomorrow. We haven't really come across them yet. But one of the things he's done, as I remember it, is have a really clever representation of expressions that are fast to evaluate. And we haven't really thought about that deeply for Idris. We've just got the term representation. And that term representation is not necessarily ideal for evaluation. So there's some things that we may be computing again and again that we shouldn't have to. I'm kind of inclined to say that could be somebody's PhD. If someone's looking for a PhD topic, then you'd have to check what Andras has done. So there may be a lot of things that have already been figured out, but scaling it up to a full language will present some interesting challenges. And maybe it's the topic, maybe it's a project that someone has been looking for. Who knows?
A question: what are your ideas about the front end with dependent types in effects?
Oh, I say these things because I like to go for walks around my home in Cooper at the minute, because there's not really much else to do, and these ideas pop into my head, and I think, oh, that'd be brilliant, but I don't have time to do it myself. So I haven't necessarily thought this through. I would just like something like that. So what do we think? What sort of thing would it have? So I've done a little bit of thinking about what effects might look like in Idris, and I've always tried to do it without extending the surface language. But then you look at other languages that really do think about algebraic effects, so things like F, things like Frank, and they have a nice syntax for saying what an effect interface is and what a handler interface is. And whenever I try encoding them, I have to do these things as functions or as interfaces and implementations, and they just don't look nice. And if they don't look nice, we don't really have any hope of them being things that programmers will want to use. Programmers will typically want to use things, I assert, that are first class in the language. And if you've got some funny library that requires you to do a bit of meta programming, for example, or some elaborator reflection, they're probably not going to use it. So putting more thought into what that syntax looks like, and having a high level construct that says this is an effect with this interface, and this is how you handle it in these contexts, that might be a nice thing to do. So what are my thoughts? I haven't really had any. It's a half-baked. It's not even a half-baked idea. It's like I've kind of just put it in the freezer, and I'll put it in the oven a bit later on. It's that level of baked. So you are free to use your own creativity and skill and judgment on that one. Don't feel restricted by anything that Idris itself does or anything I might have said, because the fact that TTIMP is there as a small language with data declarations and functions means that you can be as creative as you like in translating down to it.